Okay, today we're going to start our next topic, which is on banked curves. This is going to be a lot different than things we've been talking about so far in circular motion, but there is going to be a nice, very convenient formula we're going to cover that's going to make this a lot easier than a lot of the stuff we've been doing so far. So today's plan is we're going to start by reviewing vertical circular motion problems from the last class. There were two different kinds of vertical circular motion problems we dealt with. There were roller coaster type questions. These were ones that didn't have a tensional force. They had a normal force instead. And then we also had bucket of water type questions where we had like a bucket of water and we're swinging it around in a circle. There was a tensional force in these questions. In other words, a force that was contained in the rope or the string or whatever was holding the object that we were spinning around. Really, between roller coaster type questions and bucket of water type questions, there's not a lot different. It's more just what we're looking for in those questions. So I don't want you thinking as if these are two totally separate kinds of questions altogether. They're still dealt with in the same manner, but we're going to review and we're going to make sure we understand how to deal with each type. Then, of course, we're going to introduce how to deal with banked curves. That's our new topic for today. A banked curve is pretty much exactly what you're seeing in this picture right here. It basically just is where we have some sort of a curve that something's moving along that has a slope to it. Now, if you think about what we've been doing so far between vertical motion and horizontal motion, this has like a little bit of both components to it. There's a vertical piece up and down, and there's a horizontal piece side to side. But fortunately, you don't actually have to break it apart into X and Y components like we did back in kinematics. There's actually a really straightforward formula that can just be used to solve all these problems all at once. So when we get to it, I'll show you what that formula is and we can go from there. So first we're going to review a roller coaster type problem. Just pause right here so you can take some notes. Okay, so the question is, suppose a 85 kilogram passenger is on a roller coaster. The radius of the loop is 25 meters. If the roller coaster is traveling at 26 meters per second, find the apparent mass of the passenger at the top of the loop. So it's really important to note that we're actually looking for the apparent mass here, not just the apparent weight, and there is a difference. Remember, mass is a unit measured in kilograms, and it's the same no matter where you are in the universe, whereas an apparent weight depends on things like what gravity exists in the location you're at, or what kind of a force is being exerted on you. Like if you're in an elevator, you're going to experience a different apparent weight than you would elsewhere. Apparent weight would be measured in newtons. So since we're looking for an apparent mass, we need to make sure our final answer here is in kilograms. Now, because we have vertical motion, we can see that this is at the top of the loop. At the top of the loop, we have to be very careful as to where our forces are. Now, the most obvious force acting on this roller coaster, or the person, the 85 kilogram passenger, I should say, in this roller coaster, is the force of gravity pulling them straight down. It's not a very good straight line. It's kind of hard to draw on the computer here, but you get the idea. The force of gravity straight down is acting upon them. But we have another force that's also acting on them. And this force is something that you might not necessarily expect, but it would actually be your normal force. Now, traditionally, when we dealt with normal force, the normal force was always, at least on a flat surface, equal to your force of gravity. But in these kind of circular motion problems, the normal force is a little harder to predict. So again, the normal force would also be pushing straight down because the normal force is actually the force of the track pushing against the passenger in the roller coaster. So both of these forces, the normal force and the gravitational force, are both pointed to the center of the loop of the roller coaster. Now, the reason that this is important is we need to set up an equation involving our centripetal force. A centripetal force always exists whenever there's an acceleration for something moving in circular motion. And our centripetal force is always pointed to the center of rotation. Well, very conveniently, you notice both our force of gravity and our normal force are also pointed to the center of rotation. So if we think about how we can break down our centripetal force, Fc, since both the gravitational force and the normal force are both pointing to the center of the circle, we can say that our centripetal force is our gravitational force plus our normal force. Now, the normal force doesn't have a formula directly attached to it, at least not in circular motion. However, our force centripetal and our force of gravity do have their own equations. Now, the centripetal force, let me remind you up here, the centripetal force is mass times the centripetal acceleration. Now, the centripetal acceleration is a bit of a wild card because there's actually two different formulas that exist for it. If you take a look at your formula sheet, which I'll do right here real quick, we can see the two different formulas for centripetal acceleration are v squared over r, so your velocity squared over your radius of your circle, or this is also equal to 4 times pi squared times r divided by the period, which is capital T, squared. And remember, the period is just another way of saying how long does it take for one full revolution to be made. Now, in this question, between these two formulas, we're actually going to have to use this one for centripetal acceleration because we know what our velocity is and we know what our radius is. But if I hadn't given you a velocity, if I had instead given you the time period, you would have actually used the other formula instead. So to break down this FC, we can write this as the mass times the centripetal acceleration, which is v squared over r. This is going to equal your force of gravity, which is just the same old mass times the gravitational field strength, plus the normal force, which is hard to calculate on its own. We'll just have to get it from the rest of this formula. So in our formula we've established using our centripetal force, we can now see that we need a mass, a velocity, a radius, and of course the gravitational field strength to be able to complete this. The good news is we have all this information. The mass is 85 kilograms. The velocity is 26 meters per second. So I'll say 26 and then I'll square it. Don't forget to square it. And then divide it by the radius, which is 25. This will equal the mass, which is 85, times the force of gravity, which is 9.81. Sorry, not force of gravity, gravitational field strength, my mistake, plus the normal force, Fn. Calculating this through, we're going to get this side of the equation is 2,298.4, and that's going to equal this piece, which is 833.85, plus your normal force. Now to get your normal force all by itself, we need to subtract that 833.85. That's going to give me 1,464.55 equals your normal force. So I'm going to pause it right here. This is the normal force, which is another way of saying your apparent weight. It's a force in newtons. I should really write newtons here. It's an apparent weight. We are looking for our apparent mass. Now, apparent mass, again, is just what you feel that your mass would be in a situation like this. Now, how we perceive our mass is based around the gravitational field strength of Earth of being 9.81. That's what we base how we feel our mass around, right? Or if there was a bathroom scale sitting underneath you while you're on this roller coaster, the bathroom scale is going to be spitting on a number in kilograms, explaining what your mass would be. In other words, we can take this weight in newtons and we can realize this as a force, and your apparent mass is going to come out of acknowledging that this would be based around 9.81. So even though the force normal isn't truly or inherently based around 9.81, if you want to get what your apparent mass would be out of this, we would set this as being your new force of gravity, quote unquote, not really a force of gravity, by saying it's 1464.55 equals your apparent mass, maybe I'll call it MA, times by the gravitational strength, which is 9.81. Divide by 9.81 on both sides and you're going to get your apparent mass, which I'll just call M subscript A, to equal to 3 sig digs 149 kilograms. And that would be your final answer. Now, what you might be thinking, because you might remember what we had talked about, or would have talked about prior, that at the top of a loop, your tensional or normal force is minimized. Whereas at the bottom of the loop, your tensional or normal force would be maximized. But you might be looking at this number of 149 kilograms and saying, well, wait a minute, that's a lot heavier than the person's actual mass. Well, the reality with these circular motion questions is it's not going to be like an elevator question where if you're going down, you're going to have a lower mass apparent mass, I should say, than your true mass, and if you're going up, you're going to have a higher one. In circular motion, it actually depends entirely on the speed you're going at. In this case, we're going so fast that we're actually even having a higher apparent mass, even at the top of this loop, where our apparent mass is going to be minimized. So just because you end up with a number that's higher than your true mass isn't necessarily suspicious, right? This doesn't mean we've done the question wrong necessarily. It just means that this roller coaster is going so fast that throughout that loop, you're going to feel as though that your mass is higher than it truly is. Okay, so the next problem we're going to do is another circular motion problem, but this one's going to be more like those bucket of water questions. Just pause so you can take some notes here. Okay, CJ is swinging his grocery bag full of eggs around in a vertical circle like an absolute madman. The bag of eggs has a mass of 2.5 kilograms and CJ's arm is 0.75 meters long. If the bag can withstand a maximum tensional force of 238 newtons, find the maximum speed CJ can swing that bag at. Basically, what we have going on here, I'll try to draw it as carefully as I can. We have CJ throwing the bag of eggs around in a circle. The maximum tensional force that that bag can experience is 238 newtons. From that last slide, you might remember I told you that your tensional or normal force, really it's the same way, one way or another, is actually going to be maximized at the bottom. So maximized down here, and it's going to be minimized up here. So since the bag can withstand a maximum tensional force of 238 newtons, we're going to see that maximum tensional force occur at the bottom of this circle. And the tensional force, or normal force, as would be in a roller coaster question, is always pointed towards the center of the circle, just like centripetal force would be. So I'm going to draw my Ft right here. Ft. Now the other force that would be acting on this bag of eggs would of course be the force of gravity. So the force of gravity always points straight down. So I'm going to draw it right there. Now, if we want to think in terms of centripetal force here, because in these vertical circular motion questions, centripetal force almost acts as like a net force, we can think of our centripetal force, Fc, as being pointing towards the center of the circle like Ft. So I'll say it's going to be Ft, which is in the same direction as Fc, minus your force of gravity, because your force of gravity is acting in the opposite direction of your tensional force, and your tensional force is acting in the same direction as your centripetal force. So once we have this established, we should also start establishing what our formulas are for each of these. Just like before, we're going to notice we're going to work with a maximum speed. There were two different formulas for centripetal acceleration. There was one that involved speed and there was one that involved a time period. We're going to have to use the one that involves speed in this case. So our force centripetal can be broken down once again to be mv squared over r. This is going to equal our tensional force, which is actually given to us in this question. It's 238 newtons, so I'll just write that in as 238. No formula needed. Minus your force of gravity. And your force of gravity, as always, is mass times the gravitational constants. So, or not gravitational constant, my mistake. Mass times your gravitational field strength, so m times g. Now, let's fill in the numbers that the question actually gave us, because it looks like we have most, if not all, of this information other than speed. The mass was 2.5, so 2.5 times v squared. We don't have v, but we want to find it. Divided by r, which was given to us as being 0.75, 0.75, equals 238 minus your mass, which again is 2.5, times gravity, which is 9.81. Since we're looking for v squared, I think it would be a good idea for us to clean up the right side of this equation first. So I'll leave the left side of the equation alone. Left side of the equation is still just 2.5. So 2.5, there we go. V squared over 0.75 equals 238 minus 2.5 times 9.81 actually gives us 213.475. Now if I want to get v squared all by itself, we just need to times by 0.75. So I need to multiply this over, and I need to divide this 2.5 over. So I'll times by 0.75 and then I'll divide by 2.5 and that's actually going to give me v squared equals 64.0425 approximately. And then of course if we're looking for our velocity, we just need to square root both sides. So if I square root both sides, that's actually going to bring us to our final answer. So I'll want to round to 2 sig digs as the question had. That's going to give me 8.0 meters per second. I'll put a box around that. So again, the way we tackled this question wasn't really any different than the way we tackled the roller coaster question. The only difference is you have a force of tension rather than a normal force, but it's actually still going to be pointing in the exact same way. Really, these two kinds of questions, whether it's a roller coaster kind of question or if it's a bucket of water, or in this case, bag of eggs kind of question, they're going to work the exact same way. You can still solve them just by setting up an idea with your free body diagram, as well as understanding that your centripetal force is like a net force in this case. So think about the direction of all your forces and think about whether you're adding them together or subtracting them. Okay, so for new information today, we're going to talk about banked curves. Just pause the video right now so you can write this down. Okay, so to increase the safety of highways, curves are often banked at an angle. If you're ever driving down the highway and you get to a really long, sharp kind of turn, you might notice that the road has actually been designed so it's not totally flat with the ground. They have it slightly angled. And if you ever drive on a road like this, you'll actually notice that your vehicle seems to steer itself without you even moving the wheel very much. What this does is this reduces the amount of friction required to keep the car on the road. So in other words, even in very icy conditions, if you come to a banked curve and you're going an appropriate speed, you should be making that turn regardless of how much friction your tires have on that road. Now the banking angle is the angle at which a car could round a curve and remain on the road even if the surface was frictionless. So in a completely no friction environment, theoretically you can have a banked curve designed that a vehicle coming along that road is going to stay on that road in the path that the road is going. However, it is important to note that there is a point where a car can be going too fast for the bank curve to work. In other words, bank curves are designed specially for a certain maximum speed, whereas if someone were to go over that maximum speed, there's no guarantee that they're staying on that road. Now, another thing to note is the banking angle also applies to airplanes moving through a curve in the air. So don't just think that this is just for cars on a road. If you ever have an airplane making a banked turn, so turning kind of partially on its side while flying through the air, this same formula that we're about to learn here will still apply. Now you do not need to write this slide down, so this slide you don't need to pause for this one. I just want you to remember from a few days ago we talked about horizontal circular motion. So in other words, when a vehicle is on a flat road and they have to make a turn. You might remember me telling you that when you have a horizontal circular motion, so a car on a road making a turn, that centripetal force to the center of the circle they're turning through is actually your frictional force. They're the exact same thing. Now, that was another way of saying if you have a frictionless environment, a turn like that isn't going to be possible. You would need to have friction in order to help that vehicle through that turn. Now, for banked curve problems, we don't necessarily rely on friction. We're actually going to assume that in every question we have in Physics 20, it's going to be a frictionless environment. And the reason we're doing this is we actually have a very specially designed formula that I'm going to introduce to you in just a second that is designed for frictionless environments. This way we can actually just use the same formula over and over again. If you introduce friction to the mix, it actually just makes things more complicated and there's more calculations that need to be done. And that's not part of Physics 20. So for now, we're just going to assume every banked curve problem we deal with is going to be frictionless. So here's the banked curves formula. Just pause the video for a second so you can write the whole thing down. So the formula for working with banked curves, which is unfortunately not in the formula booklet, is tan theta equals v squared divided by r times g. Now, just to break this down, theta, of course, is the angle of the banked curve, or in other words, the slope that that curve is at. V is the maximum velocity that the curve will even possibly allow. So in other words, it's the top speed that someone can go in a frictionless environment and still make it through this curve. R is the radius of the curve. So I want you to imagine from a bird's eye view, like I do from this Google Maps thing that I've just kind of put in here. If you have a banked curve, the radius is from the road to the center of what would make that road a perfect circle from a bird's eye view. And then last but not least, G is of course the gravitational field strength. I don't know if there's going to be any cases where we'll talk about a banked curve on another planet where the gravitational field strength would be different. Theoretically, I could ask that. So just usually though, as long as it's on Earth, it's going to be 9.81 meters per second squared. Okay, so we're actually going to get a practice example with this kind of problem. Just pause the video so you can write this down. So a car is rounding a 520 meter radius curve in the highway that is banked at an angle of 12 degrees. What is the maximum speed that a car could travel at and remain on the road if it was frictionless? So with all of these bank curve problems, what's really nice is you're just going to be reusing that same formula we just learned over and over again. So tan theta equals v squared over r times g. Let's identify what we have. We see that we have theta is 12 degrees. It's not really good. There you go, theta, 12 degrees. We know our radius is 520 meters. And we're looking for that maximum speed. So in other words, we're looking for v. We actually have enough information here just to throw it all into the formula and solve from there. So in other words, we can just say this is tan of 12 equals, v is unknown, so we'll leave it as v squared, over r, which is 520, times g, which we can assume is 9.81. There we go. So if we want to get v squared all by itself, we just need to times by 520 times 9.81 on both sides. What this is going to do is it's going to give us an answer of 1084.2935 equals v squared. Then of course we just have to square root both sides, and that'll actually give us our maximum speed, so we'll have to watch our sig digs. If you look in the question, technically because of this angle here, we only need 2 sig digs. So we're going to have v equals 33 meters per second. You're going to find that with these bank curve problems, it's just the same formula over and over again. So it's just an exercise of a little bit of algebra here, making sure that we know how to rearrange a formula and solve for a missing variable. We'll do one more example here now. Just pause the video so you can write this down. Okay, so calculate the angle at which an airplane would bank if it is moving at a speed of 220 meters per second through a curve of radius 4.75 kilometers. Let's write down again our formula that we use for all banked curve problems. Tan theta equals v squared over rg. Notice that we're looking to calculate the angle, so we're looking for theta this time. We know what v is, it's 220 meters per second. And then our radius is given to us as 4.75 kilometers. Now the one thing I need to give you a heads up on is when you're using this formula, just like any other formula, you need to make sure your units are matching up. Kilometers are not matching up with meters per second, so let's change this 4.75 kilometers into meters before we even begin. So to turn that into meters, of course, there's 1,000 meters in 1 kilometer. So 4.75 kilometers would be 4,750 meters. This instead is going to be the number that we use in our formula because it matches the same units as our velocity, which was meters per second. So throwing these variables in here, we know we have tan theta, we just have to leave that like that, equals v squared, which is 220 squared, divided by r, which is 4,750, times by 9.81. When you put this in your calculator, just because I've seen it before, make sure you're really careful with this denominator piece. Sometimes what really helps, because we're going 220 squared divided by both of these, it's a good idea to put an extra set of brackets around the entire denominator as you're dividing it through. So if you do that, you're going to get tan theta equals about 1.03868. I just kept as many decimals as I was comfortable with. And now we want to get theta all by itself. Now theta is locked away inside this tan here, so to get rid of the tan, we have to take the inverse tan of both sides. So in other words, we can say theta equals the inverse tan of 1.03868. And if you throw that in your calculator, you're going to get theta equals to 3 sig digs in this question, 46.1 degrees. So again, pretty much the exact same as the last question, we just had a different variable we're looking for. With banked curve problems, you just have to know to use that formula. And remember, tan theta equals v squared over rg is not a formula that's on your formula sheet. Don't ask me why, it's just the way it is. Alberta Education just didn't put it on there. You are going to need to remember this. And the good news is the more questions you do, the easier it will be for you to remember this. So for practice, I want you to do the Uniform Circular Motion vertical booklet that was handed out last class. Be sure to complete every single question and check your answers on this. It's really important to understand to have a full mastery of all of this material before we move on. So make sure you're spending your time wisely. I would recommend that we pause the video here and just leave this up for the rest of class. And if you need any help, please let me know.